You know how sometimes you're trying to get information quickly, maybe from different places, different apps? Well, behind a lot of that is something called text embeddings.
Yeah, they're fundamental to so much modern natural language processing. Things like retrieval systems, even content generation, classification, lots of things you probably use daily.
But here's the tricky part we want to dig into today. Different AI models, trained differently, create these embeddings, but they're often completely incompatible.
Right. Even for the exact same piece of text, the numerical representations of the embeddings exist in totally separate vector spaces. You can't just compare them side by side.
It's like they're speaking different dialects of the same language, maybe, which makes combining their knowledge really hard.
Hmm. Or maybe even different languages altogether based on totally different internal grammars.
Okay. But there's this interesting idea floating around, the Platonic Representation Hypothesis. It suggests that maybe, just maybe, these big AI models are starting to develop a kind of shared, deep understanding of meaning underneath it all.
And this research we're looking at pushes that idea further with what they call the strong Platonic Representation Hypothesis.
Stronger how?
Not just that this universal structure might exist, but that we can actually find it and, crucially, use it to translate between these incompatible embedding spaces.
Without needing any shared examples or specific training data that links them.
That's the claim. And the method they developed to do this is called vec-to-vec.
So our mission for this deep dive is to get a handle on how vec2vec pulls this off, translating between AI models without a common dictionary, essentially.
And we'll explore what that capability unlocks, especially around understanding, well, potentially even extracting information from data where you don't initially know the language it's written in.
Okay, so let's start with the core idea, this universal latent representation. What is that exactly?
Think of it like finding a hidden common dimension or a shared abstract space. The embeddings from different models might look scattered and unrelated initially.
Like in that figure 1 they show.
But after vec2vec does its thing, the idea is that corresponding embeddings from different models end up really close together in this new latent space. They become aligned.
So vec2vec is kind of learning this universal translator, finding the Rosetta Stone for text embeddings.
That's a good way to put it. And the strong hypothesis is that this Rosetta Stone can be discovered and used without needing any parallel text, any direct pairings between the model's outputs.
How does it manage that unsupervised translation? Where did the idea come from?
Well, the researchers drew inspiration from a couple of areas. One is aligning word embeddings across different human languages, finding commonalities between dog in English and chien in French without needing a bilingual dictionary initially.
Okay.
And also from work in unsupervised image translation, like turning a photo of a horse into a zebra without having perfectly matched horse-zebra pairs.
Interesting. So what techniques does vec2vec actually use? You mentioned adversarial losses.
Right. Adversarial losses are key. It's a bit like having two systems competing. One part of vec2vec, the generator, tries to create translations that look like real embeddings from the target model space.
And the other part?
The other part, the discriminator, tries to tell the difference between the generated translations and the real thing. This competition pushes the generator to get better and better at making realistic translations.
Like an art forger trying to fool an expert?
Kind of, yeah. And then there's cycle consistency.
You mentioned that earlier. How does that work here?
So imagine you translate an embedding from model A space to model B space. Then you immediately translate it back from B to A using the same system.
Okay.
Cycle consistency loss penalizes the system if the final embedding isn't very close to the original embedding you started with in model A. It ensures the translation journey doesn't just lose all the original information.
Makes sense. It has to be a meaningful round trip. What does the actual structure, the architecture of vec2vec look like?
It's got a few main parts. First, there are space-specific adapter modules. Each model's embedding space gets its own adapter.
To tailor the input.
Sort of, yeah. To transform the embeddings from their original space into that universal latent representation we talked about.
Okay, then what?
Then these transformed embeddings go through a shared backbone network. This is the part that extracts the common underlying features, the core meaning independent of the original model.
The central engine.
And finally, there are output adapters. These take the representation from the shared backbone and translate it back into the specific vector space of whichever model you're targeting.
Input adapter, shared understanding, output adapter. Got it. The paper mentioned they use MLPs, multi-layer perceptrons, not CNNs like in image stuff. What's that?
That's an important point. Images have spatial structure, right? Pixels near each other are related. CNNs are great at capturing that local structure.
But text embeddings.
The dimensions in a text embedding don't usually have that kind of inherent spatial relationship. Dimension 5 isn't necessarily closer in meaning to dimension 6 than it is to dimension 500.
Ah, I see.
So MLPs, especially with things like residual connections and layer normalization, are more flexible for finding complex relationships across all the dimensions, which is better suited for the way meaning is encoded in text embeddings.
Okay, so that's the structure. How does it actually learn during training? What's being optimized?
The optimization involves minimizing several loss functions simultaneously. We've touched on the adversarial life-making translations look real and cycle consistency ensuring the round trip works.
Are there others?
Yes. There's also a reconstruction loss. This is simpler. Just encode an embedding into the latent space and immediately decode it back to its own original space. It should ideally be identical.
So ensuring the encoding-decoding process itself isn't lossy for a single model?
Right. And one more crucial one. Vector space preservation, or VSP.
VSP. What does that preserve?
It aims to maintain the relative relationships between embeddings during translation. If two documents are semantically very close in the original space, their translations should also be very close in the target space.
Ah, so it's not just translating points, it's preserving the constellation, the map of meanings.
Nicely put. It tries to keep the geometry of the semantic space consistent.
Okay, that sounds like a comprehensive learning setup.
Ah.
How did they test if all this actually works? What kind of data did they use?
They use quite a variety. For the main training, they use data from Natural Questions NQ, which is basically questions people ask search engines and the corresponding answers found on Wikipedia.
Standard benchmark stuff.
Yeah. But for evaluating how well it worked, they used a separate part of NQ, plus completely different datasets to test generalization.
Like what?
Things like tweet topic tweets, categorized by topic. Also, pseudo-re-identified MIMIC3, which involves anonymized medical records, and even the Enron email corpus.
Wow. Okay, so queries, tweets, medical notes, emails. That's a pretty diverse mix. Different styles, different topics.
Exactly. The idea was to see if the learned translations held up across different domains.
And what about the AI models themselves? Which embedding models did they try translating between?
They used a real range of them, too. Models like GTR, E5, GTT, which are based on architectures like T5 and BERT. Also Stella, which is Roberta-based, and Granite, another transformer model.
Any others?
And importantly, CLP. CLP is interesting because it's multimodal. It's trained on both images and text. So they were testing translation even into and out of a space that understands visuals too.
So different architectures, different sizes, different training data, even different modalities with CLP. That really puts Vec2Vec through its paces.
Definitely. The paper has a table laying out the specifics of each model.
So how did they measure success? What metrics tell you if a translation is good?
They looked at three main things. First, mean cosine similarity. This basically measures the angle between the translated embedding and the true target embedding. Closer to 1 is better means they're pointing in almost the same direction.
Okay, how similar are they?
Second, top 1 accuracy. After you translate an embedding, you look at all the embeddings in the target space. Does the single closest one happen to be the correct corresponding embedding? You want this to be high, ideally 100%.
Did the translation land right next to its true counterpart?
And third, mean rank. Similar idea, but instead of just asking if it's number 1, it asks, on average, where does the correct embedding rank in similarity compared to all the others? Lower is better here. A rank of 1 is perfect.
Got it. So similarity, hitting the bullseye, and average ranking. What did the results show? Did Vec2Vec manage to translate effectively?
The results look pretty strong, actually. Across various model pairs, they reported high cosine similarities, often getting up towards 0.9 or even higher in some cases.
That sounds very close.
And the top 1 accuracy was frequently very high, sometimes hitting 100%, meaning the translation landed closest to the correct target embedding every single time for that test set.
Wow. And the mean rank?
Consistently low, often very close to 1, indicating the correct embedding was almost always ranked right at the top.
So the numbers suggest it's doing a really good job of mapping embeddings from one space to another accurately.
Yes, the quantitative metrics were quite compelling across the board.
Did this hold up on those diverse datasets, the tweets and medical records? Or just on the question-answer data it was trained on?
That was another key finding. The performance largely held up on the out-of-distribution data, too. It suggests the translations it learned weren't just specific to question-answering formats, but were more generally applicable. Domain agnostic, you could say.
That's significant. It implies it learned something fundamental about the language, not just the training task. What about translating with CLIP, the image text model?
That also works surprisingly well. Vec2Vec was able to translate between text-only embedding spaces and CLIP's multimodal space, and according to their results, it outperformed other baseline methods they compared against for this specific task.
Okay, so the translation seems mathematically sound and robust, but does it actually preserve the meaning? Can you still understand the original content from the translated embedding?
That's the million-dollar question, isn't it? The researchers tried to assess this semantic preservation using a couple of different techniques.
What did they try?
First, they did something called zero-shot attribute inference. The idea is you take the translated embedding and you compare its similarity to embeddings that represent certain attributes, like topics or categories.
And see if you can predict the attributes of the original document just from the translation.
Right. And the interesting finding reported in the paper, in Table 5, was that Vec2Vec's translations often allowed for attribute prediction that was as good as, or sometimes even better than, using the original embeddings in the target space, directly what they called an ideal zero-shot baseline.
Better? How can it be better?
That's a bit surprising, but it might suggest the translation process somehow enhances some certain signals or reduces noise relative to specific downstream tasks like attribute prediction. It was particularly notable even with the MIME's medical data, predicting diseases from translated embeddings.
Diseases that weren't even in the training data.
Correct. Descriptions of diseases that the model hadn't explicitly encountered during the Vec2Vec training phase.
That really does suggest the core semantic information is getting through the translation process. What was the other method they used?
The second was embedding inversion. Essentially, trying to reconstruct the original text, or at least some of its content, directly from the translated embedding.
Trying to reverse engineer the text? How did they do that?
They used a zero-shot inversion method, feeding the translated embedding into a large language model and prompting it to generate text that might correspond to that embedding.
And could they recover information?
They evaluated this on the Enron email dataset. The findings, illustrated in their Figure 5, show that for some model pairings, this process could successfully extract identifying information or key details from up to 80% of the emails, just based on the translated embeddings.
80%. Just from the embedding vector translated from another model.
That's what their analysis indicated. Figure 6 gives examples, things like names, email addresses, dates, even financial details were sometimes recovered.
That's quite something. It powerfully demonstrates that the meaning isn't just loosely preserved, it's encoded strongly enough to be partially reconstructed.
It certainly points that way. The researchers also situate Vec2Vec relative to other work on aligning representations or bridging modality gaps, emphasizing that the key differentiator here is doing it unsupervised, without needing those parallel data points.
Okay, let's try to wrap this up. What's the main takeaway from all this Vec2Vec research?
I think the big takeaway is that it provides pretty strong evidence for that strong Platonic representation hypothesis, at least for text models. It shows it seems possible to find and learn a kind of universal language for text embeddings.
A language that lets us translate between different AI minds, so to speak, without needing a pre-existing dictionary.
Exactly. And this opens up possibilities for connecting systems, analyzing data from diverse sources, maybe even understanding data from models where we don't fully know the internal specifics.
The aha moment for me is this idea that maybe, deep down, different advanced AIs are converging on a remarkably similar way of structuring the meaning of text, even if their surface languages, their embedding spaces, look completely different.
That's the core insight, isn't it? That the underlying semantic structure might be more consistent than we thought.
And the research touches on what this might imply, for instance, regarding security.
Yes, the embedding inversion results definitely raise points there. If you can translate embeddings from an unknown model into a known space and then extract information, it suggests that just having access to the embeddings, say, in a vector database, might carry risks. An adversary could potentially learn to translate and probe them.
So even if the raw data isn't stored, the embeddings themselves might leak information after translation.
That's a potential consequence highlighted by the inversion experiments.
Okay, so maybe a final thought to leave our listeners with. If these different AI models, built by different teams with different data, are somehow developing this shared semantic structure, what does that tell us?
That's a deep question. Does it suggest something fundamental about how information and meaning must be structured to be efficiently processed? Could we leverage this convergence to build more capable, more interconnected AI in the future? Perhaps even bridging gaps between text, image, and other modalities more seamlessly.
Lots to think about. It feels like we're just scratching the surface of understanding the internal worlds of these AI systems and how they might, perhaps inevitably, find common ground.